Welcome to this explainer. Let's just jump right in, shall we? Today, we are taking a complete journey. We're starting from the very beginning, handling raw, messy data, and going all the way to the advanced, highly quantitative world of financial risk modeling. If you want to truly master data analysis, you really have to understand this entire pipeline, and that is exactly what we're going to build together today. So here is our roadmap. To successfully wrap our heads around the complex mathematical distributions we'll see at the end, we've got to build a rock-solid foundation first. We'll quickly cover categorizing data with NOIR, organizing quantitative data, interpreting contingency tables, selecting the right visuals, calculating measures of dispersion, and finally, skewness, kurtosis, and finance. Section 1. Categorizing data with NOIR. This is the very first step every single analyst has to take, identifying the exact nature of the raw inputs sitting in front of them. Now, the absolute crucial point here is data taxonomy. You can think of this as the foundational architecture of statistical modeling. In quantitative research, understanding your level of measurement is literally the most critical step in your analytical design. Because look, if you apply the wrong mathematical formula to the wrong data type, your software might still run it, sure, but it's going to instantly spit out flawed, completely meaningless results. To prevent those kinds of disastrous errors, we have to draw a hard line between our data types. On one side, we have qualitative or categorical data. This uses natural language or categories that don't have any inherent numerical value at all, like eye color. On the flip side, we have quantitative data. This is inherently numbers-based and mathematically measurable, like someone's height or their daily calorie intake. We break these down even further using something called the NOIR framework. NOIR stands for nominal, ordinal, interval, and ratio. Nominal data just gives things names, meaning you can really only calculate a mode, the most frequent item. Ordinal data introduces a rank, like letter grades, meaning we can now find a median. Interval data gives us equal distances between points, like temperature and Celsius, which allows us to add and subtract. And finally, ratio data introduces a true absolute zero, like a bank account balance, unlocking your ability to use all math, including multiplication and ratios. Okay, moving to section 2, organizing quantitative data. So once we've identified our data as numerical, we've got to structure it. Because let's be honest, raw quantitative data is completely unmanageable. You can't just stare at a massive spreadsheet of 10,000 numbers and magically spot a trend. Instead, we have to carefully organize it into a frequency distribution. This clearly tallies up the occurrences of our data within specific intervals, showing us both the raw count and the relative frequency, or the proportion, of the whole dataset. But how do we decide what those intervals should actually be? Well, we follow some very precise steps. First, we establish mutually exclusive bins, so absolutely no data point overlaps two categories. Second, we use established mathematical guidelines like Sturgis's rule or Scott's rule to find a uniform bin width. Third, we generally target between 5 and 12 bins for optimal density. This prevents our data from looking either too overly smoothed out or wildly choppy. And finally, we round to one more decimal place than our raw data to make sure we preserve true resolution. Section 3. Interpreting contingency tables. Let's pivot slightly from single quantitative variables to analyzing the relationship between two qualitative categorical variables. Take a look at these raw counts of survival on the Titanic broken down by passenger class. Now, while raw numbers give us the total frequencies, for instance, we can see 203 first-class passengers survived and 122 died, they don't immediately reveal the true dependency between those variables, simply because the total number of passengers in each class varies so wildly. To actually uncover the relationship, we must calculate the conditional distributions across the columns. Basically, we look at the percentages. Once we do that, the stark dependency is instantly revealed. 62.5% of first-class passengers survived, compared to only 25.2% of passengers down in third class. And that right there is the pure power of a well-made contingency table. Section 4. Selecting the right visuals. Because once our data is perfectly organized into tables, our next analytical step is to accurately map it to human cognitive perception using graphics. So the critical question we always have to ask ourselves is, how do we choose the right chart? How can we guarantee that our visualization actually clarifies the data for people, rather than distorting it or accidentally misleading our audience? It all comes down to a few very precise design rules. First, maximize the data-ink ratio by removing all unnecessary clutter. Just keep it clean. Second, never use 3D pie charts. The perspective heavily distorts the true size of the data slices. Third, always ensure your bar charts start the numerical axis at 0 to avoid visual manipulation. And crucially, your visual design must respect that underlying NOIR taxonomy we talked about earlier. For example, because interval data is continuous with no gaps, you use adjacent bars in a histogram. But for nominal, categorical data, you use regular bar charts with clear spaces between the bars. Section 5, calculating measures of dispersion. Now, I know the math we are about to look at might seem a little intimidating at first glance, but please, just take a deep breath. I am going to walk you through this very calmly and clearly. It's just a few simple steps, and you are going to do great. You see, when we calculate a mean, an average, we are really just creating a gentle expectation of what will happen. But as we all know, reality is rarely exactly average. So the true question we are asking when we measure dispersion is simply, how wrong can our expectations be? Dispersion just gives us a very reliable way to understand how widely our reality might vary from our best guess. Let's look closely at standard deviation. It's beautifully simple, just a 4-step process. First, we calmly find our mean. Second, we take each individual observation, subtract our mean from it, and square that result so that any negative differences become positive. Third, we carefully add all those square differences together. Now, here is a very important gentle adjustment. We divide by n-1, which is known as Bessel's correction. We do this to ensure we don't accidentally underestimate the true risk hiding in our sample. Finally, we just take the square root, and there it is. You've just calculated standard deviation. Section 6, Skewness, Kurtosis, and Finance. Welcome to Advanced Risk Modeling. We've just explored the second moment of a distribution, which is dispersion. Now, let's softly break down the third and fourth moments used in advanced quantitative analysis, taking it one careful step at a time. The third moment is called skewness. Skewness gracefully measures the asymmetry of our data. Notice that mathematically, instead of squaring the difference from the mean like we did before, we cube it. We raise it to the third power. Because we cube it, negative deviations actually stay negative. This wonderfully reveals whether our data's distribution leans heavily to the left or to the right. And the fourth moment is kurtosis. Here, we simply raise the deviation from the mean to the fourth power. When you raise a number to the fourth power, it heavily amplifies the extreme outliers. This quietly tells us about the tails of our distribution. It shows us if our data is leptokurtic, meaning it's highly peaked with very fat, risky tails, or platykurtic, meaning it's flat, steady, and peaceful. Let's softly look at how these complex-looking formulas actually help protect us in the real world of finance. For instance, negative skewness shows us when tracking stock returns that our mean is being pulled down by large negative drops. Target semi-deviation lets us gracefully isolate and calculate downside risk strictly below a specific target, like 20%, so we only worry about the times we actually fall short. And leptokurtic risk tells an investor that fat tails exist, meaning extreme catastrophic market crashes might actually occur much more frequently than a normal bell curve would ever suggest. These formulas are really just helpful tools to let us realistically anticipate danger. And that brings us to our final thought for this explainer. We have journeyed all the way from identifying raw nominal data to mathematically defining the shape of catastrophic portfolio risk. But I want you to ask yourself, does your past data truly predict the exact shape of your future risk? These statistical tools brilliantly structure our understanding of the past, for sure. But true mastery as an analyst requires taking these models and anticipating the unknown. So keep questioning the data and keep learning.